Where is everybody else? T09. Something is not right. So the 4 folks that can hear me now, I may be hanging up on you and restarting the meeting because something's not working right. But I'll wait a few more seconds before I do that.
Hello.
Oh, there you are.
Yeah, I hit the join, but there's like 6 joins you got to hit.
It's working funny right now. So it's amazing you got there at all. So cool. Like this morning, if you wouldn't mind, can you do that example on the machine defects before
Sure.
we do the actual lab? Other than that, same as before. I got the recorder on already, I think. Yes, I do. It's recording already. I'm going to go ahead and give you control. And I will listen for a while, but I'm going to leave a little early today. So
Okay.
just hang up when the time's up and it should auto record.
All right. How many have we got? 8. I'll wait for a little bit.
Yeah, there were about 20 in the live session, so you should get at least 12 or 15 will probably show up. Although you're competing with a beautiful sunny afternoon after 2 weeks of everybody being cold. So
I know, right? It's so nice that we're painting the outside of the house.
yeah, so yeah, good luck on winning that battle, but do the best you can, okay?
Okay. Okay, so since 1, this is being recorded, and 2, there's a little more to get to today. We're going to go ahead and start here. And the first thing we're going to do is a example from the lecture. And before we actually get to the example, it's important to note, and you can actually see the back of the page here. So we're trying to run a hypothesis test. What are the elements we need? Well, we need something that we can test, meaning we need a sample. We also need a hypothesis that we can either accept or reject. And finally, we need to specify what are the conditions on which we reject. So the rejection area is this shaded area here. So we can slide it to the left or slide it to the right. And it's on both sides, by the way. Okay, so our example is, we got a machine in a factory that makes widgets. And every time the daily production has at least 10% of defects in the widgets, you need to take it apart and take the machine apart and service it and all that fun stuff. So randomly, 100 items at the beginning of the day showed up having 15 defective widgets. So the foreman claims that the machine needs to be taken apart and repaired. Does the sample evidence support the foreman's assertion? So It might not. We need to plug in all of our values in order to figure it out. What the real question would be is, we pulled 100 and we got 15. So 15 exceeds 10%, but is 100 enough? Is 100 enough to trigger that? So let's have our random variable y, and this is going to denote the number of defective widgets. Y is going to be a binomial, so it means everything is either true or false, meaning the widget's defective or it's not. The probability of one outcome is going to be p, and the probability of the other is going to be 1 minus p, because everything has to add up to 1. So let's say the defect outcome is p. We're going to assume that 100 is large enough so that we can approximate what we want to do with our z-score statistic. So we have our null hypothesis where if things are over 10%, if the number of defective widgets is more than 10%, then we need to take the machine apart. We're going to reject that if the p-value exceeds it. Okay. So in order to do that, the last things we need to plug in is our test statistic. So this is going to be the actual item we're looking at versus the average divided by the formula see here. It's not super important that you actually know what the formula is. Just know that this is the z statistic we have. And our rejection region is going to be any time that z is larger than z alpha, with alpha referring to this value here. So we're going to choose alpha to be 0.01. So the question is, what's the value for z alpha? Don't know. Well, thankfully, we don't have to do a whole bunch of math to figure it out. What we can do is let the computer do that math. So I've copied the code from here to here, and we're going to run it. So what we need to figure out is, this is going to reject or fail to reject based on whether z-test is greater than z alpha. So we're trying to figure out what z alpha is by trial and error. So what do we think we should start with? Well, we can calculate z alpha, but we still need to check it out from trial and error. So let's start out with this value. So if we use the z alpha value of 2.32, we get a do not reject the null hypothesis. And what was our null hypothesis? Oops, wrong one. Saying that we do need to take it apart, so that is the sample evidence supportive of the assertion that we need to take it apart? Well, if the z alpha value that we chose, and here's a way to visualize it once it gets done running. So we can see the z alpha value is going to be in this region, and we see enough of it being to the left that we don't really want to reject. However, if I change this like that, we've gone from failing to reject the null to rejecting. And as we can see, the visualization does change a bit. So as before, we had, I wish I could get them side by side. Make a note of where the things on the x-axis are. So from 0 to 0.2 is where all the elements are. So this is a histogram. And most things are in the 0.1 range. But if we change this to 1.6, we can see that we have more things going into up towards the 0.3 area. Now we could change the amount of times we actually do the sample, but this isn't actually part of the lab, so I'm going to get to the lab. This is something from the lesson that admittedly I hadn't been super prepared for this morning. So just kind of running through it. If you want, you can change these values just to see how this might change the way the histogram comes out. Okay, let's get to the actual lab itself. And what are we going to be doing in the lab? Well, statistics, of course. What we're going to be talking about today is confidence intervals. So when you have a confidence interval of, say, 95%, it's not saying that 95% of everything falls in my interval. It's saying that, let's see. When I have my normal distribution, I'm saying that with 95% confidence, I'm going to have something in this range rather than something in the outliers. And my assumption is that something's in this range, meaning like my assumption is I'm going to have not enough items to want to take apart the machine, and that will be the range here. Or you could say that I'm flipping a coin 1,000 times and I'm recording the number of heads. The idea that it's a fair coin is going to be in this area, and the result that it's not a fair coin are going to be in the outliers. All right. So first example we have, we are going to talk about how many people in the nation of Italy love soccer. Well, how many people are there in Italy? We're going to use the number 60 million. So the real question, how many people in the 60 million population like soccer? They either do or they don't. There's no in between. Now there is an actual number of the 60 million people who like soccer, but we don't know what it is. The number exists, but it is impossible from our perspective to know. Well, why is it impossible? Because we can't really just go and ask 60 million people. Moreover, this is just an example. From our perspective, we can't have total knowledge about pretty much anything. That's why we even say that the idea of a confidence interval. You can't truly know whether a coin is fair or not, because you can't look behind the fabric of reality to see, is this coin got all the correct variables and all the right gravitational constants and everything. Only a omniscient being can know that for sure. You can only know the true value of something if you aren't looking at something from our mortal perspective. But it is useful to know that the true value exists out there somewhere, and that we are going to want to approximate it. So that's what we're going to do. First thing we're going to try is, let's assume we can actually know everything, know every true value all the way down to the nitty-gritty. So let's assume that. Let's suppose we know exactly that the number of people in Italy that love soccer is 75%. So let's get our variables in place. We know the total population, 60 million. We know the percentage of people who love soccer is 0.75. And then we can say the population that loves football is the total population times 0.75. And then the total population that doesn't is going to be everything 1 minus that, right? Next thing we're going to do is we want to make a NumPy array with 60 million elements. So each element in this array is going to represent a person from this population. Every person is going to have a 1 or 0 assigned to them. So that person has a 1 if they like soccer and 0 otherwise. Okay, so let's do that. What we have now is a 60 million element array. And we can check that here. Yep, 60 million. And what is the average of my entire array? Well, since it's nothing but ones and zeros, if it were halfway filled with ones and halfway filled with zeros, we would get 0.5. But since it's using this ratio here, we get the same ratio out, which makes sense. I take a bunch of ones and zeros, add them together, and then divide by the number of total things. I should get it right back. So that's exactly what we were hoping, which is good. Now, what we're going to do is I have my entire list of people, 60 million of them. And what I'm going to do is I'm going to take out 1,000 of them at random. I'm going to get all these 1,000. And I'm going to see from those 1,000, since I'm choosing them randomly, how many of them like soccer. And because we built this out of ones and zeros, all we have to do is take the average of our sample. Okay, so I take 1,000. All right, well, of that 1,000, I got 76.2% of the 1,000, which would mean what, 762 out of 1,000 like soccer. Okay, that's fine. But we do know for a fact, because we're assuming we know everything, that the true value is 75. So why did we not get 75? Well, it's because, let's say I have I know for a fact that I have a truly fair coin, which would mean it's equally likely that I flip and I get a heads, or I flip and I get a tails. Is it still possible to get 2 heads in a row? I flip a coin twice. Is it possible to get 2 heads? Well, yes, it is, because the first flip could be either. The second flip does not depend on what the first flip was. They're independent. So it's 50-50 each time. Now, if I were to flip that coin 2 times, 1,000 times in a row, and I were to get 2 heads every single time, I would not believe that whoever told me this is a fair coin was telling the truth. And so as we can see, if I run this again, pick another 1,000 randomly, this time I get 765. Do it again, I get 74.3. Do it again, I get 73.4. I'm just randomly picking 1,000. Okay, well, instead of me just hitting this button a million times, let's put that in a loop. So I'm gonna do it 10 times. And as we can see, since I'm picking from this 1,000 of random, I don't get the same one every time. But you notice that they kind of tend to revolve around the 0.75 area. Now, what would happen if I did more than 10? Or what if I were to average all these together? What's the result I get? Well, let's try that. I'm going to take 10,000 samples. Instead of 10, I'm going to take 10,000. And then what I'm going to do is I'm going to take my 0.72 and my 0.74 and my 0.748, and I'm going to add all these together. And then I'm going to divide by how many times I did the loop. So if I were to do that for the one we just had here, the average of everything I got was 0.7504, which is pretty darn close to the actual average that we know it is. 0.7506, 0.7514. The less times I do this, the more likely it is that I'm going to get something further away. Why is that? Well, as I said, I have a fair coin. Is it possible for me to flip it twice and have 2 heads? Yeah, it's possible. And if I'm only doing that event of flipping it twice one time, that's the only thing I have recorded. So if I flip the coins twice and I get 2 heads, and that's the only time I ever do it, all the knowledge I have is that the likelihood of having a head is 100. But that's why I do the coin flip experiment more than once. And in this example, our experiment is grabbing 1,000 people. So we're going to grab 1,000 people 10,000 times, and we're going to average them all up and see what happens. All right. So we did it 10,000 times, added everything up, and the likelihood of a random person liking soccer from our 60 million population, as we've approximated it, is 7.75002, which is very close to the true value that we knew because we assumed we knew this. So we're assuming we have total knowledge and that the true value is 0.75. Well, this is pretty darn close. So the more samples I take, the more likely that my average of my samples is going to approach the true value. And I'll illustrate that again. So remember that the experiment we're doing, so a sample is getting 1,000 people. So I just got 1,000 right there. How many like soccer? 74.6%. So now I'm going to take the average of all of these, but I'm only going to do one. So what's the average of one? It's just the value itself, 0.76. And there's no variance in a sample of one. Okay. Well, now I'm going to do two of these. I'm going to do two samples. My average was 0.74. Okay. And now I do have a true variance, but it's not really that useful. Well, let's do 10. Like 0.742. Now I know in the back of my mind that the true value is 0.75. And what we'll start to see is the more samples I take, the closer the average is going to start approaching the true average. So let's do 1,000. 0.751, this is 75.1%, 74.9%, 75%. But if I crank it up to 10,000 like it was, we see that we really are just hovering around that 75%, which is the true ratio. Let's plot all of this. And I'll put this down to the 100 again. Now, when my numbers are low, so 100's kind of low, doing this 100 times isn't that impressive. We can see that our the plot we get is kind of normal looking, but it's lumpy. I'll do it again. Okay, it's still normal-ish looking. Still kind of lumpy. Let's crank the number up. So from 100 to 1,000. All right, that's less lumpy. Still, hey, that was pretty good. But it's still not completely symmetrical. Well, you may notice that the more I crank this to higher number of samples, the more normal it starts to look. Well, what if I do something truly absurd? What if I take 1 million samples? That's what we're going to do next. Now, if you've caught on to the pattern here, if I could do this forever, if I could do this an infinite amount of times and actually get it to come back, what we will get is the actual normal distribution. So if you're playing this in God mode, you can actually do this 1 million times, or I'm sorry, an infinite number of times to get the true number. But we can't do that. But what we can do is do something quite large, which is 1 million. We're going to do the yank 1,000 people out of the 60 million 1 million times. So this will take a while, so I'm going to run it and keep talking. You may have noticed as I crank the number up from 1 to 2 to 10 to 100, the more the values started to encroach on what the true number was. And how do we know it's the true number? Because we assumed it was from our God mode perspective. And once I was getting to 10,000, and it was getting really difficult to not arrive at the 75 mark. But we were still getting a lumpy distribution. I ran this 1 million times. Let's see how close it is to the actual normal distribution. And remember, the normal distribution looks like this. Now, granted, I'm not the best artist, but it is truly symmetrical on both sides, and it's got a curve in the middle. It's still running because that's how many. We're doing 1,000 people out of 60 million 1 million times. It takes a while. All right, We're done. Now let's plot it. This will also take a while. And again, when you're doing this, these are warnings, so don't worry about it. When everything's in white text like this in a red box, it's generally a warning, and it also have warning in the message. So it's not that something's going wrong. You can just ignore it completely, kind of like these. All right, so this distribution here is as normal as you're going to get. It is practically indistinguishable from the normal distribution. All right, so this is the best approximation we're going to do of how many people in Italy love soccer. Turns to be a mean of about 0.75. And that's the one we truly know it is. But we're still trying to approximate. We can also look at a box plot to see that the 0.75 is the mean. And if we go one standard deviation in either direction, we get somewhere like 0.74 something and something like 0.759 something. Okay, any questions about what we've been doing so far? The more we crank up the number of times we do the sample, the better results we're going to get. Well, all of this was done with the knowledge that 0.75 is truly the average. But what if we don't actually know that for sure? Which is the case. We don't actually know the numbers we're looking for before we go looking for them. Well, let's do that instead, because that's what we actually have to do. I don't know before I set out on my experiment that the value is 0.75. I don't know. So let's run in the miserable world of not actually knowing what these values are. Well, let's start out with what we do know. We just took a sample and we got 70.73. We also know that the normal distribution behaves like this. It is symmetrical on both sides. We have the mean in the middle. And if we go out a standard deviation in either direction from the middle, we get some regions. You can recall back to some quartiles. This is kind of like that. So I'll return to the coin flipping example for a second because it's easier to talk about. I flip a coin, let's say 10 times. That's the experiment. And I record how many times does the coin come up heads. So a truly fair coin should have a likelihood of coming back 5 out of 10 times. Now this is going to give us, it's terrible. It's better when I go fast. All right. So 5 is going to be the true value that should be in the middle. But it's possible to get a result where I got, 3 out of 10. But what I can say is 5 is the mean. And I have a value that is the standard deviation. I don't know what it is off the top of my head, but it's some value. And that value is called sigma. Well, it's labeled by sigma. That's what the standard is. Mu is used as the mean and sigma is used as the standard deviation. What I can do is I can go out one standard deviation in either direction. And so let's say it's 1.5. So 1.5 from 5 in either direction is going to give me like 3.5 to 4.5, which you can't really get 4.5. I'm sorry, 3.5 to 6.5, but you can't really get 6.5 flips. But what I can say is, if I did this 1,000 times, the coin 10 times, and I do that 1,000 times, 68% of all my results should be somewhere between 3.5 and 6.5. Why do I know that? Because of this fact right here. You take the mean and you go one standard deviation in either direction, no matter what the mean and no matter what the standard deviation is, if it's a normal distribution, which most things are, and everything we're giving you an example to do right now are normal, including the Italy thing, 34% of everything is going to be in this one, 68% of everything is going to be in this one standard deviation region. If I go out 2 standard deviations, I get 95% of everything. So 95% of everything, every sample I do is going to be 2 standard deviations within the mean. So that means only 5% are going to fall outside of 2 standard deviations. So if I take my mean, go 2 standard deviations in either direction, I only have a 5% chance of getting anything outside of that interval. And 95%, 2 standard deviations is the standard. It's what's used almost all the time. So this brings up a concept of margin of error, because it is possible to get an erroneous reading. And I think in another lab, we're going to go pretty deep into that. We do have a margin of error formula. Looks like this. It's not super useful to just look at the formula because we can visualize it instead. So let's say I'm going to choose my alpha regions to be very specific. So I'm going to say only 5% of everything is going to make me reject. Okay, I can do that. That gives me a larger area from my mean to the area to where I'm going to reject. And that means my margin of error, which is this, so the length from here to here is exactly this. So if my margin of error is large, it means I've got a smaller alpha, which means I'm more specific in what I'm going to reject. If I'm less specific in what I'm going to reject, my margin of error is smaller. Now, there's no correct way to do this. You, depending on what you want, to be more specific and have a larger margin of error, or less specific in a smaller margin of error. What's more important, getting a very specific test or having a small amount of error? You kind of have to weigh them and choose. There's no broad answer to that. Okay, let's actually do the example with all of that knowledge. Okay. Another warning. It's busy. It's going to plot something, so just hold on. So returning to the sample we got. If we took a sample of the 60 million, so took 1,000 people out of the 60 million and got 73%, we can say that we're 95% confident that the real percentage is between 70%, which is 73 minus 3, and 76%, which is 73 plus 3. So someone tell me, where the heck did I get this plus 3 and minus 3? Where did this 3 come from? The measure I got was 73, and I'm going to the left by 3, and I'm going to the right by 3. But where did this 3 come from? Why did I choose the 3? And there's only like 3 people here, so I recognize Carson. I know he's usually good about answering. So where does this 3 come from? I wouldn't be doing my job if I didn't ask you guys at least one question. I would like more, but you can't always get what you want. We're adding plus or minus 3 onto 73. 73 was our measurement. So where did the 3 come from? So Robert says those are the number of standard deviations away. Yes, this is 2 standard deviations. 95%, the reason I know it's 2 is because of this fact here. Every normal distribution has this. 95% is 2 standard deviations. So yeah, the standard deviation for this was 1.5. It's way up at the top. But this is 2 standard deviations in either direction. So what I can say is, even though I don't know the true value, which is 75, I can say with a 95% confidence that the true value is somewhere between 70 and 76, which just so happens to be true. It just so happens that 75 lies in this interval. But it's not a pure coincidence. What is the likelihood of getting this interval so low that we would be incorrect? Well, the standard deviation isn't going to change, which would mean we have to go 2 to the left to get this to be wrong. So we would have had to have received a 71%. Well, what's the likelihood of getting 71%? Well, it's right here. 71 is right here. And you can see how much of this is under that curve. Not very much. And the same thing would be here. So we would need to either have taken 1,000 people and gotten 71% or 79%. And that's not very likely. In fact, we have a 5% chance of getting those. So I could do this 20 times and maybe once, maybe I would have got one of these. So if I were to do, that's why you do the experiment, you know, you have a large number of samples. It is almost impossible to have chosen one of these outliers 10 times in a row. Okay, so we have the confidence interval. That was the thing we wanted. We have our confidence interval that it's 73 plus or minus 3. And how confident are we? 95%. And since we don't actually know the value, this is the best we can say. But since we cheated a little bit and used the information that we shouldn't have, we know that the 75 is in there. So we would have been correct. Let's do another example. From a normally distributed population, all of the stuff we've just been talking about only works on the normal. So we have that. We randomly took 500 students with a mean score of 461 on the math section of the SAT. Suppose the standard deviation is 100. What is the estimated true population mean for the 95% confidence interval? So what this is asking is, we know this is a normal distribution. We have that. We want to know what is the true mean. We don't know what it is. What I can do is I can take a sample and I can get a mean. It'll be something like that. Who knows? It could be there. It could be there. It could be anywhere, really. It could be there. But what I want to do is I want to have an interval here where I am 95% confident that 2 standard deviations in either direction. So let's say I got my measured mean. What did it actually end up being? 461. So I'm going to have a mean that I calculate. And I want to be 95% confident that the true mean is somewhere in this region. So that's what we're going to do. I want to be 95% confident that the region I'm about to draw has the blue line in it somewhere. So what's the only way that the blue line won't be in there? Well, if my measured mean is like somewhere way over here and 2 standard deviations only takes me like this far. So the region would be like this, and it would not actually have the true mean inside of it. Okay, so first, let's get all of our data in. Our sample size is in. The mean we got from our sample is 461. The confidence level we want is 95. Standard deviation we said was 100. And then we have the z value associated with this. What's the z-value? Where did we get this? This is the last question I'll ask you guys. So someone tell me, where do we get the z-value? Well, I'm actually not going to tell you. And in order to do the homework all the way through, you need to know how you get the z-value for a given confidence level. So if you work with me, we can figure it out. I will continue through with the 95% confidence level example. And if we get through with it and haven't heard anything, okay, well, that's just going to be the way it is. All right, so what I will say is for a confidence level of 95% and these values, the z-value for what we want to do is 1.96. So I'm going to calculate my margin. And we have the formula for that. It's right here. So I have my z-value, I've got my sigma, and I've got my sample size. All right, z times standard deviation divided by square root of my sample. So what's my margin of error? Margin of error is 2.77. Okay, that tells me the direction to go. Or not the direction, the distance to go. So what I can say is that with a 95% confidence, the mean will be captured within the area somewhere between 76.2%, or not percent anymore, are we? We're oh, right, yeah. So in somewhere between 76 and 72. Oh, I didn't run this again. I was like, why is that number like this? Earlier, I did the next one. So let me run them all again. It's like that number doesn't make any sense at all. All right, here we go. That looks better. So the true population mean, the one we don't know, the one you can only know if you know everything, with a 95% confidence is somewhere in here. It's between 452 and 469.7. And I know that with a 95% confidence. Okay. So this next exercise is actually in the homework. So we're going to run through, like I said, at least the 95% version of it. So from a normally distributed population, we took a sample of 200 dogs, and the mean weight was 70 pounds. Suppose the standard deviation of the population is 20. Question 1. What is the estimated true population mean for a 95% confidence interval? Well, this is easy. We just did this. We just need to change up the numbers. What's the sample size? It's 200. What's the mean we got from our sample? It was 70. What's the confidence level? It's 95. All right. What's our standard deviation? It's 20. Now, what is the z-value for a 95% confidence interval? It's 1.96. How do you know that? Well, I told you I'd tell you one of them. Okay, so let's run these. Margin of error is going to be 2.77. And this was the number we saw earlier. So running one of these tests is super simple. You just plug in the values. Only hard part is actually doing the sample and getting, the mean. So we had 200 dogs, and let's say that the 200 is not the number of dogs in the population. That is the number from the sample we got. Let's say we have a population. I don't know how many dogs there are in Lubbock. We'll guess 20,000. I don't know. Well, I took a sample of 200. Why? Because, well, it's expensive to do these studies. I don't have the money, the time to go measure every dog. By the time I measure the last dog, the first dog might have gained weight or lost weight. Who knows? But what I can do is I can go do 200. 200 is what my budget allows me to do. So I measured 200 and I got an average of 70 pounds. Okay. I want to be able to say with 95% confidence that the average weight of all dogs in Lubbock is in some region. So what's that region? Well, it's this. So the true value of all the weight of dogs in Lubbock is between 76.2 pounds and 72.7 pounds. And I'm 95% confident on that. Okay. This next example was from Wednesday. So I'm going to skip through that one. But there is another one down here. All right. So Amazon is considering changing the color of their logo. They're not really. This is just the example. So they might change the smile from orange to green. Let's assume they had 5,000 users. They sent 2,500 to site A and the rest to site B. In the first group, 1,863 users made a purchase. In the second group, 1,904 made a purchase. Now, obviously, 1,904 is more than 1,863. But just like I can flip a coin twice and get two heads in a row, I can also, I've only done one sample because they only had the time to do one sample. They took 5,000, split it in half, and this is the numbers they got. So I can't just say 1904 is greater than 1863 and it's worth the money to change the logo. But what I can do is run an A/B test to see if this value is statistically significant enough to make the change. Well, luckily we already did one of these. It was here. Right here. So everything we did for the first button, second button, we just need to do for Amazon. And since this is actually the one from the homework, like this is the question, I'm not actually going to run the numbers because that would just give everything away. But what I will do is run back through what we want to do. So I take the numbers that were sent to the first option. I take the numbers that were sent to the second option. I got my purchase rate. And then that'll give me the ratio. So the rate at which people from the orange smile bought something and the rate from the green smile. And you don't have to print them out. I just always do so we can see them. And then, if you recall, we did a whole bunch of visualization that led to right here where it said, yeah, we can visualize all that stuff if we want. But really all you need to do is run these two things here. So this function we have, it takes 4 arguments. Those arguments were found here. It's just plugging in the numbers. So I plugged in the numbers. Let's say I plug them in for the Amazon numbers. I'm going to run this, and that will get me the number I need here. And then I can just say and run my Whitney test to see if it works, or to see whether I should change the smile or not. And that actually covers everything in the homework. So question 1 is the dog example. I've already done the first one. Since I didn't really get much about the Z value, everything except, I mean, you could go ahead and run it with the Z value for the 95%. That's totally something you could do. I'll warn you, for those who are here and paying attention, or those who are watching this and actually paying attention at this point, don't do it. Why am I able to find it. Oh yeah. Because the z-value for a 95% confidence interval is not the same z-value for a 90% confidence interval. I'll just tell you right now, it's not. So don't do that. I'll even tell you what you can search for. So z-value formula, it's in the lesson, but if you search z-value formula, you'll be able to figure it out. So everything is already done for 95. Do everything the same way for 90 and 99. Just make sure you change the numbers correctly. Exercise 2. You're going to have a CSV, and you're just going to be making some visualizations and getting the mean standard deviation. And you're going to be doing the same trick for 95 and 99%. And then the exercise 3, I just showed you everything. So that one should be super easy. And we're exactly at 5:50. So does anyone have any questions before I let you go to go enjoy the first nice weekend of the year? All right. Well, everyone have a good one.